clear. Okay, so we started already with ionic and covalent bonding last time. And as I have told you, okay, ionic is for metals and nonmetals, while covalent is for both nonmetals. So ionic bonding is the attractive force that, chemical bonding is the attractive force that hold the atoms together in a substance. So you have the ionic, covalent. So ionic metal, non-metal, covalent is both non-metal, and metallic is within the metals. Okay, and the ionic bond is usually formed when there is a positive and a negative charge that is formed between the ions once they exchange electron. And the positive and the negative charge led to this electrostatic attraction called ionic bond. And you are also introduced to this so-called Lewis electron-dot symbol, wherein we can put the number of valence electron in the form of like this at the side of the chemical symbol. So the most that you can occupy is 8, which represents the number of electrons around the stable elements, which are the noble gases. Okay, so if we look at the example that we have before, we work on calcium oxide, wherein we see the transfer of electrons from the metal to the non-metal. And we also discuss, okay, the energetics of the formation of ionic compounds. So usually we take into consideration the ionization energy and electron affinity, and then added it with the lattice energy to give you, okay, the energy that is needed to convert a non-metal and a metal to an ionic compound. And we call it the Born-Haber process. And we also discuss Coulomb's law, with respect to how strong the ionic bond will be and how it will affect the physical properties of ionic compound. So in the Coulomb's law, we just stated here that the higher the charges, the higher is the force of interaction, and the smaller the radius, the higher is the force of interaction. Okay, and we also said that whenever there is an exchange in the electron, most of the element tend to gain the electron configuration similar to that of the noble gases. So if I'm not mistaken, we end up with this one, okay, where we said that if we have a transition element, the outermost element that lost, the outermost electron that's lost are the one that is found in the s orbital and not in the d orbital. So let's try to continue on with the ionic radius. So how is this different from the atomic radius? So the difference is this one is when the atom is in ionic form. So if you're going to look at the ionic radius, you just look at the size of the spherical region around the nucleus of an ion within which the electrons are most likely to be found. And while ionic radius, like atomic radius, can be somewhat arbitrary, it can be measured in ionic compound. So what's the rule do you think that we have in ionic radius? So this is the two rules that you need to know. Okay, whenever you lose an electron, the cation that formed is always smaller than its neutral atom. Does it make sense?
Yes.
Okay. Yes, because if you're going to look at the electron configuration of the two, you lose not only the electron but the 3s orbital. Okay, so you lose the s orbital there because there's no more electron that occupies the s orbital. Now, on the other hand, an ion is always larger than its neutral atom. Now, the question, does it make sense? Okay, here you're losing electron. Here, an electron is added. So when an electron is added, okay, the charged particle is much larger or bigger than the neutral particle. Now, I want you to look at this. So what can we say about Na plus? What noble gas has the same configuration as Na plus? Anyone? If you're going to look at the periodic table,
Helium?
it's the same as neon, right? And if you're going to go further, it's also the same as F minus. So when you have F minus, you also have, if you're going to look at the electron configuration to this is just 1s2, 2s2, 2p6. So F minus has that configuration, neon has that configuration, and sodium ion has that configuration. So if elements and ions, okay, has the same electron configuration, the term that we have there are used is isoelectronic. So when they are isoelectronic, refers to the different species having the same number and configuration of electrons. They just have the same electron configuration. So Ne, Na plus, and F minus are isoelectronic. Why? Because all of them has this configuration. Now, what does this mean? Are they the same in everything? The answer is what?
No.
Are they the same in terms of the other properties?
No.
The answer is no. They are only the same in electron configuration. But if you're going to look at it in an isoelectronic series, okay, ionic radius decreases with increasing atomic number. So what does it mean? What if I ask you to rearrange them in terms of ionic radius? Which is the largest? How are you going to arrange them?
Sodium?
So I can arrange it like this, but how will I going to put the relationship if I have it this? Is this more than or less than or equal between the two?
Sodium is greater than neon?
So is sodium plus more than or less than neon in terms of ionic radius?
Less than.
Because it says here, increasing atomic number, ionic radius decreases. So this is a higher atomic number than neon. Okay, and fluoride would have be bigger than neon. So what does it mean? So the higher the atomic number, the smaller is the ionic radius, if they are isoelectronic. I have another example here. So using the periodic table only, arrange the following ions in order of increasing ionic radius. I want you to study on this for the exam. Okay, the trends that we have there, the atomic radius and the ionization energy. So if you're going to look at this, how are we going to arrange them? The first question, are they isoelectronic? Are they isoelectronic? So from the look at it, if you're going to look at, so this is Br minus, this is Se2 minus, so most likely they are isoelectronic. Okay, they have, if I'm not mistaken, try to look. I'm not sure if it's argon. Okay, so I'll try to look. I need my periodic table. Okay, so if I'm going to write this one, yeah, this is argon with 4s2, 4p6. That's there. electron configuration. So if we're going to arrange them, so all we need to do is look at this. So following the statement from the previous slide that says here, ionic radius for an isoelectric series decreases with increasing atomic number. So right away, the smallest would be,
SR.
okay, the SR2 plus, followed by
BR.
Br minus and Se2 minus. This is not included in the exam, but you have a topic in chapter 8 regarding strengths. So those are the type of questions that come out. Okay, so remember that. So if you're just listening, I'll tell you, you're not going to fail the exam. So if you cannot listen, you can always go back to a recording. Okay? Now, we're done with the ionic bond. So let's go on the other bond. Okay? So covalent bond is a chemical bond formed by sharing a pair of electrons. So to consider how this covalent bond forms, we can monitor the energy of two isolated hydrogen atoms as they move closer together. So you have what? H2. So if you're going to look at it, there's like that one. So maybe we can put there the nucleus that they have. Okay. So the way that they do is the energy decreases first gradually and then more steeply to a minimum. As the atoms continue to move closer, it increases dramatically. So you have to look at the distance between the atom when energy is at a minimum. So this is how, if you're going to look at the energy with respect to the distance between the two nuclei. Okay, so if you're going to start making this closer to one another here, so they will go to a portion where the potential energy is at the lowest. And if they become more closer, the energy starts to go up. So this is, okay, the most stable form. And the length that corresponds to that is usually your bond length. So that is the length wherein the two hydrogen atoms are stable. So higher or lower than 74 will give you a much higher energy. So when we're looking at stability, we're looking at the lowest energy that you can have. Okay? And that is how your covalent bond is formed. So usually that length, that refers to the distance between the two hydrogen atom where a covalent bond is formed. So if you're going to look at this, you have a hydrogen atom and then a hydrogen atom. At that distance, there will be bonded together. So as the hydrogen atoms move closer, the electron of each atom is attracted to both its own nucleus and the nucleus of the second atom. So that's what it means. Okay? But you can represent this using what? The electron-dot formula. So we already worked on this electron-dot formula earlier, right? In the ionic bond. Now, how do we work on this in the covalent bond? So usually, when you form an electron pair, that's two dots that is formed. So an electron pair that is between two atoms is a bonding pair. And it can also be represented by one line for each bonding pair. So if we have one hydrogen, how many dots do we have? Anyone?
One.
One.
Okay. And if we have another hydrogen, there's also
One.
one. Who's that? So, what happened? One and one, okay, they form into an electron pair. A pair is always two, right? So, that electron pair that we have there, that is your bonding pair. So, instead of writing it as two dots, you can write it as one line. One line is represented by two dots. And that is your bonding pair. Okay? Now, there are also electron pairs that are not bonding. And we call them either the non-bonding pair or lone pair. But for hydrogen, we only have one dot from each of them. So what happened is, okay, we shared. So that's how they share the electron. So from one original electron with another hydrogen, each of the hydrogen now is sharing two electrons. That's why you call covalent bonding as sharing of electron. Okay. Now there is a specialized covalent bond. One of them is the coordinate covalent bond. So when you have a coordinate covalent bond, this is formed when both electrons of the bond are donated by one atom. So what does it mean? Okay. When in the case of hydrogen reacting with ammonia, so if you're going to look at the thing here, ammonia would be represented like this. Or maybe I just put it in terms of, okay, so you might say, where did I get this line? So remember, two electrons represent a line, or two dots represent a line. So what happened? Okay, so the hydrogen has one. So when you have a coordinate covalent bond, so what happened here? Both electrons of the bond are donated by one atom. So it goes to that one. And when it goes there, you have this. If you're going to look at this, you have for this, and for this, and you still have there. And that's the one that will bind with H plus. It's like an ionic bond, but not really ionic bond because it's not a metal and a non-metal. This is the case where a hydrogen is transferred to another atom. Okay, and when that happens, you form a charge. Now the thing is, once you're shared here, so if you're going to look at the two electrons forming the bond with the hydrogen on the left, were both donated by nitrogen. So once shared, they are indistinguishable from the other NH bond. Okay, so that's one specialized, we could say, covalent bond. But if you're going to look at whether they are ionic bond or covalent bond, they follow the so-called octet rule, the rule of 8. Okay. Now you may ask, why 8? Anybody? I answered it from our previous lecture. Why 8?
It shows the valence shell.
Okay, that's the valence shell. Why 8? Because that is the what? Noble gases. That's the number of valence electrons of the noble gases. So the octet rule states that in forming covalent bonds, atoms tend toward having a full 8 electrons in their valence shell. This tendency is called the octet rule. So in the octet rule, atoms tend to form covalent or ionic bonds until the outermost shell contain 8 electrons. Now the hydrogen is an exception, the hydrogen and the helium. What's the number of electrons that they can form at the most?
2.
Okay, they can only form 2 because they're just the s orbital. In the first period, you only have one s. Do you have one p? Is one p present?
No.
Okay,
No.
no. So you only have the s orbital there, so you can only accommodate 2. So instead of the octet rule, there follow, if you sing with one with another person, the duet. Okay. So hydrogen and helium, they don't follow the octet rule, but they have this duet rule. Okay. So what does this mean? Whether you're covalent bond or ionic bond, your outermost electron should have at the most 8 electrons. And that is similar to the noble gases. Okay? Now, before we go further, we go to another specialized covalent bond. So how do we look at the bond between this one and this one? So both of them are covalent bond. Okay? So when do we have the so-called polar covalent bond or the so-called polar bond? So a polar bond is a covalent bond in which the bonding electrons spend more time near one atom than the other atom. So if I'm going to ask which of the following exhibited H bonding or polar covalent bond, A, B, or C?
C. C.
If I'm going to ask this question, which of the following exhibited polar covalent bond?
All of them?
So all of them are covalent bond, but only one of them is a polar covalent bond. Look at the definition, in which
C.
the bonding electrons spend more time near one atom than near the other atom.
C. C.
Okay, so if we're going to look at this with A, all of them are the same. F, and then F. Hydrogen, both of them are hydrogen. Now, hydrogen and fluorine, that's where one of them will be getting the electrons more toward itself than the other atom. Okay, so this is the one that exhibited the polar covalent bond. Now, how do we know this polar covalent bond? You have to know the concept of electronegativity. And you can relate electronegativity to the size of the atom. So if you're going to look at the definition here of electronegativity, it's a measure of the ability of an atom in a molecule to draw bonding pairs or to draw bonding electrons to itself. So this is the ability, okay, of an atom to attract toward itself the electrons in a chemical bond. So my question now is, which do you think is a higher electronegativity value? The smaller atoms or the bigger atoms?
The smaller atoms?
Smaller atoms. As it says here, electronegativity is related to ionization energy. Who has high ionization energy, the small or the big atoms?
Small.
Okay, the smaller atoms usually they have a high ionization energy. Now imagine if you're smaller, that means you can attract your electron. Just says, hey, come here, right? So the attraction is much higher, or the electronegativity is much higher. And if you're going to look at the trend, because you're the atom telling, hey, electron, come here. Okay, you can do that if you're a small atom, but if you're a big atom, maybe just like you, my student, when I say, hey, listen, not all of you will listen. Okay, so if you're going to look at this electronegativity value that they have, they are assigned. So this is what you have. You don't include the noble gases. So it's just until group 7. So what does this value means? That's the electronegativity value. And for you to determine if you have a polar covalent compound, all you need to do is compare the difference between the electronegativity values of the elements in a bond. So what can you say the electronegativity difference between fluorine and fluorine and hydrogen and hydrogen? They are both what?
Diatomic ions.
Okay, yeah, they're both diatomic ion. But if you're going to compare the electronegativity difference of this one, what do you have? You get 0. Why? Fluorine minus fluorine, that's 4 minus 4. Hydrogen minus hydrogen, that's 2.1 minus 2.1. But what if you have it here? What is the electronegativity difference? So it will be 4.0 minus 2.1. So you have there an electronegative difference of what?
1.9.
1.9. And if you have a value of electronegativity difference, that means you're a polar bond, or your bond is polar. Make sense?
Yes.
Yes.
Now, you can only have a polar bond if there is a non-zero value. If the value is equals to 0, so that is really a covalent bond. But if the value is non-zero, it is a polar covalent bond. But there is also a difference. Let's say, how about this? What's the electronegative difference of NaCl? So all you need to do, 3 here, and then
Negative.
here. So you have what?
2.1.
Minus 0.9, you have 2.1. No, you always go with the higher minus the lower.
But they
Now,
are
this is the thing. What's the information that you can get from the electronegativity difference? Okay? If the difference is equals to 0, so you have there a covalent bond. Now, if the difference is higher than 2, what do you have? Maybe we can do it here. So the difference is very large, you have an ionic bond. And the limit that they have is what we call higher than 2.0. When the difference is large, the bond is polar. So that is between 0 to 2.0. If it's 0, okay, that is just non-polar covalent bond. This is polar covalent bond. And this is ionic bond. So those are the information that you can get in the electronegativity difference. So the difference in the electronegativity between the two atoms in a bond is a rough measure of bond polarity. Okay, so what does it mean? So if we go with ionic compound, what do we have in ionic compound? Anyone? Yes, if it's more than 2, it's ionic. What do we have in ionic compound? Anyone?
A metal and a non-metal.
Yep, aside from that, what do we have?
A transferring.
We have charges, right? So when the electronegativity difference is more than the 2, that means there is a positive charge and a negative charge.
Negative charge.
Now, how do we associate that to a polar covalent bond, like HCl? We don't have a charge, but we have the so-called partially negative and partially positive N. Now, the question is, between H and Cl, where is the partially positive and where is the partially negative N?
Would hydrogen be partially positive?
Okay, so you do it like that. And this is like this. And if you are asked the direction of the electrons, you're going to draw it like this. So what does this tells us? The arrow direction points us where the electron is going. And this one here, just like Kylo Ren's cross sword, it tells us that this is the partially positive N. So what guides us that the electron goes to chlorine instead of hydrogen? Anyone?
Chlorine has higher electronegativity.
Very good. That's why I'm putting you back here. So the one that has a higher electronegativity value, it is the one that will get the electron. She's the one that will say, "You're mine, electron, come here." So that's what it means by electronegativity. It will get the electrons from the other atom if it has a higher electronegativity value. Is that clear?
Yes.
Yes.
So
Yeah.
let's see if you understand. Let's try to answer this thing, although the answer is already there if you have the slide. So using electronegativities, arrange the following bond by order by increasing polarity. So when you say you have a positive and a negative charge, that's really very polar. I don't know if you heard the use of polar aside from science this lately.
Do you want it from decreasing from the least to most?
It will be in order of increasing polarity. Okay, but just to give you a hint, you don't only use this in science or in chemistry. You're using it right now. They said the people are just too polarized. What does this mean? If you heard the news, okay, they will say, oh, the people at this time is too polarized. So it's hard to those on the left to listen to those on the right because they're so very what? Different in ideology. Okay? So when you're talking about polarity, so usually if you have a positive and a negative charge, most likely you're the most polar. Okay? So if you're going to look at this, all you need to do is go here in the previous slide that contains the value, but I think I already put some of them here. So this is what you get. Okay, so increasing polarity, so that means the lowest electronegativity difference to the highest. So I will start with this one, right? The Cn, followed by the OH and the NAF. And if you're going to look at the NAF, this is already what? That's the ionic bond already. So if you have an ionic bond, that's really two polar. Okay? So OH is more polar than CN because of the values of their electronegativity difference. That makes sense? Huh?
Yes.
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 So the more polar it is, that means the more or the larger is the difference between two elements. The non-polar, there's no difference. Okay? So let's go now to the main topic that we have, not only in chapter 9, but also in chapter 10. Okay? And I think you need to do this at least in chapter 9 and chapter 10. So we have these Lewis electron-dot formulas. So what we're going to do now is how do we write Lewis symbol, or as here in the book that we're using, Lewis electron-dot formulas. In other book, they call it the Lewis structure. So how do we end up writing it like this? And this like this. So those are the example of your Lewis structure. So we're going to go on them one by one today and next meeting. So calculate the number of the valence electron. So what does it mean? You should know what's the valence electron of the given element. And then you calculate all of them that you have. Those elements that are involved in a given formula. And then you write the skeleton structure of the molecule or ion. And then you distribute the electrons to the atoms surrounding the central atom or atoms to satisfy the octet rule. And then you distribute the remaining electrons as pairs to central atoms. So let's try this one. How do we end up like this? What's the valence electron of fluorine?
7.
7. And you have there, so let's say F2. So you have there 7 times 2. 2 is the number of fluorine in the given formula. So overall, the valence electron that you have there is 14. So write the electron skeletal structure of the molecule or ion. So I'm just going to put it like that, because that's the only connection that we can get, right? Now that line costs you how many electrons?
2.
2 electrons. So that from 14, you already use up 2 to link your fluorine. So how many available electrons do you have now?
12.
12, right? So what are we going to do with the 12? Distribute electrons to the atoms surrounding the central atom. There's no central atom because you only have 2 atoms or atoms to satisfy the octet. So that means each of them should have 8 electrons. So what will I do? I get 6 on one of the fluorine, and then I get 6 on the other fluorine. So I utilize now all the 12. So what's the next thing that I'm going to do? I'm now going to look at each of the fluorine if it satisfies the octet. What does it mean? If it has 8 electrons. So I have 6 and 6 here. Now, how many electrons does the line represent?
2.
2. So that means each of them now has, if you're going to write it, this is really how it looks like. So 2 of the electrons are being shared by both fluorine. So if you're going to count those 2 for this fluorine, you're going to count those two for this fluorine. So you add it with the 6 in each of them, you satisfy now the octet. Okay? Now how about the HCl? So again, we calculate the number of electrons. Hydrogen has how many valence electron?
1.
Chlorine would have,
7.
so that means you have 8. So the connection that you have is just this. So you already utilize what? 2 electrons. And the 2 electrons already satisfy your hydrogen because hydrogen just followed the octet. Now you still have what? 6. So you distribute it to the chlorine. Oh God, why should it be this? So it's not really on the pen, it's on the user. So this is now the Lewis structure of HCl. Analyze. We're going to make a lot of that. Because the next one that we have is this. But we follow the same thing that we did there. So question before we work on those items that I've shown you.
I have a question.
Sure.
For the electrons surrounding the chlorine, is that because of the electronegativity, or?
It just happens that they have 7 valence electrons. That's why they have more electrons.
Oh, okay.
Mhm. Now, how do I'm going to write now the polarity for HCl? It will be like that. Okay. So question, before we go in more than 2 elements, because what we have now is just a binary. So let's apply this concept if we have now more than 2. OF2. So what do we do? What's the first thing that we do?
See how many valence electrons there are?
Okay, so see how many valence electrons. So oxygen would have what?
6.
And you may ask yourself, Professor, how do we know the valence electron? What is your guide?
The group.
Periodic table.
Okay, your guide is this one, the periodic table. So this is your guide. Oh no, I don't know. Here. So I have a periodic table usually that I have here. So the group number that you have there, the 1A, that is your guide to determine the valence electron. How about chlorine?
14.
So you have there 7, that's 14. So overall you have 20. Now you may ask, Professor, how do we know the central atom? So usually if you have 3 elements there, the one that is different, that's your central atom. So the skeletal structure of that would be maybe like this. So when I did the structure like this, how many electrons did I use up to tie up oxygen with both chlorine?
4.
4.
Okay, 4. So remember, 1 line, 2 electrons. So if I have that, I utilize already 16. So it said there, the next thing that I'm going to do is to distribute the electrons that I have. So maybe I need what? 6 here, 6 here. So how much I utilize for the fluorine?
12.
12. So I still have 4. So I put there the other 4. Now, what do I do next? I account for all the electrons already. So what will I do next? So the thing that I'll do next, if you're going to leave this step there, distribute the remaining electron as pairs to the central atom or atoms. But we're done. We're okay with that. So the one that we need to look now is satisfy the octet rule. So what does it mean? Each element has 8 electrons. Okay. So I have 6 here. Or I could say 3 lone pairs. So this is what we call the non-bonding pairs or the lone pairs. And I have 1 bonding pair. So a bonding pair has how many electrons?
2.
2. So 2 plus 6, I satisfied the octet for this one. The same thing with this one because they're equivalent. They have 3 lone pairs and 1 bonding pair. How about the oxygen in the middle? Does it has 8 electrons?
Yes.
Yes.
It's sharing 2 with both.
Okay. So if you're going to look at this, I have 2 lone pairs there. So that's 4. And I have 2 bonding pairs with each bonding pair having 2 electrons. So I have also 8. So that means this is now the correct one. Okay? Let's go on the next one. NF3. So how do we put this?
One N with the 3 F like coming down. It's
So
like
N is what? How many valence electron is N?
5.
5.
5. And then you have here 7 times 3, if I'm not mistaken, right? So that will give me overall 21 plus 5, that is 26 electrons, right? And what's the only possible way that we do it? You connect it like that. So how many electrons was used for the skeleton structure?
6.
6. So I can remove 6 here. So 20. And then what will I do? I'm going to distribute 6 electrons in the 3 fluorine. I really hate this. So all you need to know is there's 6 electrons in each of the fluorine. So how many electrons was utilized there?
18.
18.
6 times 3, you have 18. So you still have 2. So where do we put the 2? That's the 4th step there. The remaining electrons to the central atom. So I put it here. Now all electrons are accounted for. So what do we do now? We need to look at each of them having octet number of electrons. So fluorine, each of them are equivalent. There's 3 lone pairs and 1 bonding pair, and each pair is 2 electrons. So that makes it what? 6 plus 2. So each of them has 8 electrons. Now how about nitrogen? Does nitrogen also has 8 electrons?
Yes.
Okay. So you have there 8 electrons. So this is already the correct one. Now let's go to this one. So this is a little bit tricky. But you just follow the same principle that we have, the same step that we have. So the first thing that we're going to do, the number of valence electrons. So nitrogen is what? 5. And then 2 for the hydrogen. I mean 1 for each hydrogen.
3.
Or we could say 1. And oxygen is what?
6.
6.
6. So if we have here 5, 2, 6, 1, 14, right? So what could be the arrangement here, which could be the central atom. You can have more than one central atom here. It can be either what? Nitrogen
Oxygen.
and
Oxygen.
oxygen. So we could put it like this, and then we connect. The hydrogen to it. So in this case, how many electrons are already utilized?
6.
8.
8.
1, 2, 3, 4. So 4 times 2 will give you 8. Now, as you know, hydrogen only obeys what? Do hydrogen need to have 8 electrons?
No.
Only one.
Okay, so only one.
2.
Only two.
Okay, only 2. Okay,
Alright.
so there's 2 for this. Oops. 2 for this and 2 for this. So they're fine. How about nitrogen? How many electrons does it need to obey the octet rule?
2 more.
So right now,
4
your
more.
nitrogen has 6 electrons from the bonding pair. So it needs 2 more in the form of a lone pair. So you put that thing. So your 6 available there, 1 was used, so you still have 4. How many electrons does your oxygen needs?
4.
4. So you put there like that and like that.
I have a question. For the nitrogen, could you put a dot on the top and a dot on the bottom?
No, I mean, you can put it like this. It's fine. As long as you put the dot around the element.
Okay, so they don't have to be even?
No, I mean, as long as what we call the dot usually should be in pair.
So you can't
Unless
just...
it's one element. Okay? So I can put this dot, if I don't want it to put, I can put it here, as long as I can see 2 dots around the nitrogen. Clear? Is that clear?
Yep.
Yes, thank you so much.
Okay. So question. Before we go to the more complicated Lewis structure. So what we have here is just straight to the point. All of them following the octet rule or the duet rule. But there will come a time that there will be some exception. So usually if you have C, N, O, and F, they should always be 8. They're strict followers of the octet rule. So what does it mean? All the time, there should be 8 electrons. So I'm just going to go on the time wherein there's some stuff that you need to do adjusting in terms of the sharing of the electrons. Okay, we'll finish this slide and then we go to some review. So CO2. So what's the valence electrons that we have for CO2? So you have here what? Carbon.
4.
Okay, oxygen.
12.
So 2 times 6 will give you 12. So you have here 16. So if you're going to look at this, that's how you have it, right? So if you're going to arrange it this way, okay, how many electrons was utilized here?
4.
4.
4. So you still have 12, right? So what do you do with the 12? You distribute it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So oxygen fine for the octet. But how about carbon? How many electrons does carbon has here?
4.
4. So that means
It needs 4 more.
you need 4 more. Now the question is, where are you going to get that? So in this case,
We need to make another pair.
your lone pair can go to become a bonding pair. So what does it mean?
So would you take one valence electron from each oxygen?
Yep. So you can have here more than one bonding pair. So you convert your lone pair, maybe this one. So instead of isolating myself, what if I'm going to share it with carbon? And the same thing with this one. What if I'm going to share it with carbon? So is this a much better Lewis structure?
Yes.
So the way that you're going to do is you count. So you have here oxygen 1, 2, 3, 4, 5, 6, 7, 8 electrons. The same thing on this side. And then this one you will have here what? 1, 2, 3, 4. So each of them has 2 electrons. So you have there 8 electrons. So this is now your thing. The double bonding. Now what if you can ask yourself, what if we do it this way? Is this possible?
No, because it's not stable.
Okay. But if you're going to count the electrons that you have there, it's possible, right? How many do you have? 16. So 1, 2, 3, 4, 5, 6, 7, 8. So it is possible. But later on this chapter, okay, I will tell you why this is not possible. Why this one is more prepared compared to the other one. When I say it is possible at this time, it can account for all the 16 electrons. But later on, you will see that this is more prepared compared to that one. Okay, so let's go to the last one, HCN. So how do we assign the valence here? Hydrogen,
1,
1, yeah.
1. Carbon,
4,
4,
nitrogen,
5.
5. So you have here overall 10. And if you're going to look at this is how you're going to arrange them, right? Now, how many electrons we already utilize here?
4.
4.
4. So that means we have to distribute the 6 electrons in such a way the carbon and the nitrogen will have 8 electrons while the hydrogen has already satisfied the 2 electrons. How are we going to do that? We're going to do bonding. I mean, multiple bonding. So how do you think I'm going to distribute these 6 electrons between carbon and hydrogen? How many more electrons do they need to share? Can I make it? Okay, I put 4 here and I put the other 2 here. Does that make sense?
Yeah.
Yeah.
So if you're going to look at this, you just need to account the 10. 1, 2, 3, 4, 5. Okay? So I'll end chapter 9 at this point. We will continue on Tuesday. So what we're going to do now is your exam.
Today's review of chapter 7 and 8, or only
So
chapter
what have we learned about chapter 8? We continue the atomic structure, right?
Yes.
So we stop with the nuclear model, but the problem is it cannot account some stuff. How can it be stable? Okay, so after the nuclear model, which model came in?
Bohr's.
Okay, so you have here Bohr. So what the Bohr model tells us is electron can what? Go to a much higher energy level once it absorbs energy. And electrons can also go from a higher energy level to a lower energy level upon emission of energy. So they have their like a planetary model. Okay, so if you have an electron here, it can go to a higher one once energy is given. Or if you have an electron here, it can go to a lower energy level, one that is closer to the nucleus, once energy is emitted. So Bohr was able to explain the stability, although it's what we call application or applicability is just to the hydrogen atom. But it was able to explain why we have this so-called line spectra that we have. And it becomes precursor to the one that we have as the Q quantum mechanical model, where the orbits becomes the what?
Orbitals.
Orbitals.
Orbital. The region where you can probably find the electron. Okay? And we said the orbital is defined by what? What's Qn? Quantum numbers.
Number.
Okay? So usually they said an orbital can be characterized by what? The first three quantum number, the n, the l, and the m sub l. Although in our lecture we have it like this and this, in the exam we have a hard time finding this symbol, so we just put their l and m sub l. Okay, so don't be we could say confused on that. So what do we say about these three quantum numbers? Although we said there's four quantum numbers, the last one is just the spin quantum number, but the first three quantum number describes an orbital, right? So the first quantum number that we have there, that's the principal quantum number. It usually refers to the what? The size. So when you look at the size, the higher the number that you have there, the bigger is your atomic size. And usually the value of n is always what? Positive, right? From 1 to positive or infinity. But usually we just use until what? 6 or 7. Okay. Now L on the other hand is the
Shape.
Okay. Although we define still that with a number, L is defined as what? From 0 to
n minus 1.
n minus 1. So if L is equals to 0, we assign a particular letter to it, right? If L is equals to 1, L is equals to 2. So what do we assign for 0? What letter?
S.
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 D.
And then you have P.
D.
So what it tells us is the shape. So what did I tell you? S for spherical, P for peanut, D for double peanut. But if you're going to look at the shape, so spherical is usually like that, the S. And then the P would be like this. And then the D would be like that one. Although one of the D is what? You have a D like this one, but like a ring in between them. Remember that, huh? And M sub L would be what? Spatial orientation. So the way that you be thing is the M sub L value would depends on what? L. Okay, from negative L to positive L, including 0. So what is the stuff that you're going to do to remember here? So you might be given different quantum number, a set of quantum number. You may be asked which is permissible, which is not. You still remember that?
Could we review that?
So if we have this one, is this okay? Is this
Yeah.
okay?
I remember
Yes.
that.
How about the
Yes.
second one?
No.
No. This is a question.
No.
No, it's not okay.
No.
Okay, so this is not okay. And you should know why, right? So if you have it like this, is this okay?
No.
Yes.
Yes.
L is 0.
Is this okay?
No.
No.
Why? Remember, this value depends on
First value.
the previous one. Now, the fourth quantum number that you have there, the values that you expect is either what? Positive 1/2 or negative 1/2. So if it's not positive or negative 1/2, then that's right away is wrong. Okay? So I would suggest you, those who just joined us again today, to look at the structure. Okay, to look at the records that we have, the recording session that we have, because I cannot explain everything by now.
So if L is 0, M can be only 0, right?
Yeah, that's why this is not possible. Because if this is 0, the only value of this is 0.
0.
This is the one that make it wrong.
So
Thank
I
you.
have a question on one of the questions on the quiz today. Like,
You might have, but you remember the dry run that you have is just what? I think it has only 7 questions. You have to take it in lockdown respondus.
no, I'm asking a question about it itself, not like how to do it, like a question that was on the quiz. It asked about 2F, and then it asked about the L, like how many orbitals it would have.
Oh, we will go on that. Don't worry.
Okay.
We're still here in the set of quantum numbers.
Sorry.
Okay. So you have to know this thing here. Okay. Now you can also be asked like what one of your classmates is saying for the number of the orbitals and the number of the electrons. So how do you know the number of the orbitals if you're given the n?
You
So this
square
is just equals to what?
n squared.
That's just equals to n squared. So if you're asked how many orbitals are there when n is equals to 1, your answer would be
2.
1.
Again. Okay. How many orbitals are there when n is equals to 1?
1.
I'm talking about orbitals, okay? Okay, because 1 squared is equals to
1.
1. My God, I'm worried now. Now, what if the question is this? How many orbitals and electrons are there when n is equals to 3?
9 orbitals and 18 electrons.
So you have 9 orbitals and 18 electrons. Now, if the question that I have is this, how many orbitals are there when there is n equals to 3 and L is equals to 0? What is your answer?
You're asking the amount of orbitals and electrons again?
The number of orbitals and electron when this is given. What is
So-
your answer?
9 orbitals and 1 electron. No,
That is true if n is equals to 3, but you are given the specific
One
assumption.
orbital.
Your answer is only what?
One
1.
orbital.
Where do you base it? You base it on the value of your L. Remember, L equals to 0, 1, and 2, right? How many orbitals is L here?
One.
1. And why is 1? Because the m sub L value is only 0. How many orbitals for L equals to 1?
One.
Is it 1?
Three.
3.
3. Because m sub L is what? Negative
Negative
1,
1, 0.
and
positive
One.
1. This is a little
be
confusing.
careful. Because the thing is, you're not going to get the same question. Some of you might have a question like this, and some of you might have a question like this. But the question being asked is, how many orbitals are there when this is given?
So is it still 2 times L plus 1?
So here, what do we get in the L? I think there's a formula also there.
Yeah, 2 times L plus 1.
2 times L for the number of orbitals when L is given. So 2 times L plus 1. So there are 2 formulas there. Okay. The number of orbitals when n is just the one given, and the number of orbitals when L is given. Okay. You might have some questions like that. Or you might have a question, what is this orbital? N equals to 3 and L equals to 0. How do you write this orbital?
3s.
Very good. Or you might be given, if you're given an orbital 3s, what are the possible quantum numbers? So you're given there n, L, and m sub L. So what is the correct quantum numbers if you have a 3s orbital? So n is equals to what?
3.
3. L is equals to?
0.
0.
And m sub L is equals to what?
0.
0.
0. Those are the questions that being asked. Okay. Now for the atomic, for the periodic table, I think the only one that we will ask there is you have to find the trends if you're given a different set of elements. So you're going to what we call, you have to understand if it says 1 is the smallest and 5 is the biggest. So you have to put the element or put the number in each of the element for the sequence.
Are we allowed to use our own periodic table?
There's a periodic table that is given. My suggestion to you, do the find a 30-minute time during this weekend to work on the exam through dry run.
Okay.
There's 2 questions there, arranging the sequence based on atomic radius and ionization energy. Okay, so you have to know how to do it. And then in terms of the calculation, we're going to do it after you did your dry run this weekend. That's why I want the dry run to be done before our class next meeting, and I want the OWL to be run before your class next meeting. So any loose ends that you need to ask, we can utilize it during our review session in our class next meeting. Regarding electron configuration, I think the way that you're going to be asked is what will be the valence electron, or what is the electron configuration for this particular atom, but you have there the periodic table and you will be fine with it.
Will you ask the noble gases pseudo? The pseudo-noble.
It depends on what is being asked, because I told you what we do is we just put every question, all questions that we can have related to the chapter in the test bank, and
So
each of you will get different questions, but the same principal question.
So it's gonna be like winning the lottery if we get good questions.
I'm not sure, but all I can say is none of you will have the same question. The one that you're going to get the same is the principal. So you can have a question, what is the, which set of quantum numbers refers to this orbital? Or you can have a question, if you have this orbital, what are the sets of quantum numbers? Some sort of that. So you may be given a 3p, so that means that the answer that you have there will be what? 3, 1, and any of these what? Value. So those are the type of questions that you will have. I'm not making it available yet because I'm still trying to fix the thing. And all I can say is whatever the form of the dry run, that is the form of the exam. And I think everyone will be happy. Why? Because the way that I'm going to do the second exam, I'm going to make everything available. All questions at one time.
Thank you.
Thank you so much.
That's why if you're still going to complain here, I think I quit as your teacher because I don't know what to do anymore. Because I'm going to put everything now. Okay, so when you get the question, that's why I want you to take the dry run, because there you will see everything. The periodic table, you said 27 questions, 3 of that question, that makes it 30, are non-credited because those 3 questions contains the periodic table, the solubility rules, and some of the equation. Okay, so I'm going to put everything now. So if you're still going to have a problem, I don't know what to do.
Thank you.
It's okay. But don't be lenient, okay? As I told you in the email, I don't fail any students unless they don't do their lab and their OWL. Because those two, lab and OWL, they're what? 45% of your grade. So if you don't have anything to show that to you, how can I work with the 55 and the passing is 60? Can you take that? Can you think about that? Okay. I can only deal with the numbers that you give me. I told you, it's easy for me to fix everything in the lecture. Okay. But in the lab, okay. And I already saw some of your grades and some of you, I don't know what I'm going to do. How can I help you there? So please do your part in the lab.
I have a question. Do you
Okay.
suggest we email our lab professor because we haven't received any grades?
I would suggest you email them, and if they still don't reply, if I am your, you CC me in the email. Let's see if you still don't reply. Because for me, I usually respect the lab instructor. I don't want to do what I did last semester.